Hello students, welcome to Fundamental Physics Lab class, and today we're going to look into the Heat 01 mechanical equivalent heat. This is part of the lab offered by the Department of Physics and Science here. So the main idea of this lab is generally when we speak of energy, we could have two units of energy. One is defined by mechanical energy, defined by work. If you use a force of 1 Newton producing work for 1 meter, then multiplying Newton meter, you would get work in joule. And this is the mechanical work. And another one is the thermal energy, which is defined from the definition of temperature. So if you use the energy to heat 1 gram of water through 1 degree Celsius, then you would have the thermal energy in calories. And so if you divide the work in mechanical work with the thermal energy in calories, then you would have the conversion of 4.186 joules per calories. So today we're going to be proving this constant today. So the apparatus that we're going to have is called the Microwave apparatus. So the way it works is you're going to have a ribbon hanging onto the thing, and you're going to be measuring the force that's acting on here. So as you spin, you can see that the bob here lift up a little bit. So the force difference between the weight of the bob alone and the bob after being lifted is the friction. And this friction right here is going to cause heat in this copper piece that's sitting in the middle in the center. So in this lab, you'll be spinning this in order to create the heat, and that heat that's being generated here is going to be measured through the thermometer that's attached to there. So for data analysis part, so first of all, you need to measure the temperature. So you're going to be measuring the temperature at a given time. So from minute 0 to minute 4, the temperature is going to be constant, and that's going to be the room temperature. And then after minute 5, you start spinning. So after you start spinning, the temperature is going to increase. So the temperature here is going to read higher number as the time goes on until it reaches minute 11, where the temperature is going to start reducing due to cooling. So after you stop turning the thing, then the temperature is going to be reduced. And then the first two columns that you're going to have to fill after you have filled the temperature that you have measured is you're going to calculate the average time and the average temperature, which is quite self-explanatory. Average time is you use the upper row with the lower row, add them together, divided by 2. So 0, 0 and 1 average should be 0.5. And 1 and 2 average out should be 1.5. And then 2 and 3 average should be 2.5 right here. Same thing here. You add these two temperature and then divide it by 2. Then add these two, divided by 2, and then you get this average temperature. And then same thing here. So once you start spinning, the temperature is going to increase. So you add this number with this number, then divided by 2. So 15.1 added by 15.3, you're going to have 15 here, and so on. So you would have this column by averaging this column, and you would have this column by averaging this column here. So next, as you make a plot of the average temperature with the average time, so you have already calculated average temperature and average time. So here you would read the initial temperature, and then from graph A is what you're gonna get from average temperature versus average time. So after you stop spinning, the temperature is gonna start reducing. This is the cooling effect. So initially you would have graph A but not graph B. So we'll get to graph B in a minute. So from graph A, you can use graph A to estimate the real temperature, because as you try to heat these things up, as the temperature of the blob increases, the cooling rate also increases, because if you put like things that are hot in the ambient air, the hotter it is, the faster it's gonna cool down. So at higher temperature, this thing is gonna reduce in temperature due to the cooling effect. So to compensate for the cooling effect, you need to plot the cooling graph. And this is what I'm about to explain. So you're going to need this second graph to make this D graph. Okay, so to make this second graph, what you need to do is you need to estimate the cooling rate. So as I mentioned, the higher the difference of a temperature of an object from the room temperature or the ambient temperature, the difference is going to determine the cooling rate. So if at the beginning the copper blob is at 15 degrees Celsius, so to say. It's gonna start at 0 cooling rate, because if the thing is at the room temperature, it's just gonna sit there and the temperature would never change, right? So the cooling rate would be 0 for 15 degrees Celsius, or 15.1 in this case. So 15.1 would read 0 degree per minute. And then you need to determine what is the maximum cooling rate. So maximum cooling rate is when the thing is hottest. So right here, you have the hottest part of the measurement. So to estimate the highest cooling rate is you need to find the slope between point here and this point. So finding the slope right here, you can actually start estimating what is the maximum cooling rate. So this would give you the cooling rate at the highest temperature right here. So by doing this, you should be able to estimate what is the cooling rate between this point to this point. So this slope right here should give you the average cooling rate at the highest temperature. So from here, you can see that the cool part is gonna be 18.55 on the y-intercept, and here is 18.85 on the y-intercept. So to estimate the slope, the average temperature of these two number is going to be 18.7. So 18.7 is going to be the x-axis here. So this is the confusing part. The y-axis reading on graph 1 is going to be your x-axis reading on graph 2. This is important to remember. All right. So by estimating the average slope between these 2 point, point and actually estimate the slope of the center point here. So this is 18.7. So make 18.7 and then calculate the slope here. Let's say that you have the slope of 0.1. So this 0.1 is in the unit of Celsius divided by minute. So the cooling rate would be 0.1 Celsius per minute at this point. So you would have 2 points here. So this red point is going to give the estimation of the cooling rate here. And then the blue point, which is 0 at room temperature, you can estimate the 0 cooling rate here. So what's in between? The question is, then you just draw a straight line that cuts through here from the maximum cooling rate that you calculated from this point and the minimum cooling rate, which is 0. Then you draw the line. So after you have connected the line, then what you can do is you need to read the cooling rate at different temperature. So you're going to be reading different temperature and record different cooling rate here. So this cooling rate here is going to be used to correct for the temperature that you've lost from the cooling effect. All right, so here we need to estimate the cooling rate for each different temperature. So from the data that we already have, we have the temperature. So we actually use the average temperature here to estimate what is the cooling rate. So read the average temperature. Sorry, this red line should have been here. So read the average temperature here to estimate the cooling rate here. For example, right here you have 18.4, so you just read 18.4 is around here, estimate the cooling rate to be 0.093, so record the cooling rate here, read the temperature, and right here 15.2, you can read 15.2, which is down here, which is going to give you the cooling rate of this much. So you just read whatever x-axis and y-axis that's sitting on this line, and then record the cooling rate on this column. So once you have recorded the cooling rate on this column, next thing you need to do is to calculate the loss temperature. The loss temperature is the temperature that's lost from the cooling. So since you know the cooling rate, so at the room temperature, the cooling rate is going to be 0. So the loss temperature is going to be 0. So what you need to do is you lost 0 Celsius, and the cooling rate is 0 Celsius per minute. So 0 added by 0 is 0. 0 added by 0 is 0. So you keep doing that. And then here, 0 added by 0.003, then you would have 0.003. And then you add this column with this guy right here. So the next minute, you 0.012. So adding this number to this number, you would get this number. Then you add this number to this number, then you get this number. Keep doing that, and you would have an entire column of the loss temperature, which is the cumulative of the cooling rate, which is changing as the temperature increases. So now, you know how much temperature is lost. So you can actually do what you call the correction from the cooling rate. So you from column A, which is the average temperature, you can add column A with the loss temperature to estimate the real temperature that's supposed to be happening. So you add this number, the average temperature, with the loss temperature, and you should get column B, which is the real temperature. Once you make a plot of real temperature versus time, you can actually have a nice little straight line here. And then from there, you can extrapolate to get the final temperature and initial temperature. All right. So make this guy, this graph, and the graph is done. And next, what you can do is you can calculate delta W and delta Q. Delta W is from the work by spinning here. So the force difference is the weight of the bulb versus the reading on the scale. So if you find that difference, you can get the friction that's acting on here. And then since this guy has the diameter of d and is spun for n time, so the work there is going to be n times 2 pi r, and that's equivalent to pi d. So the work is n 2 pi d multiplied by the difference between force 1 and force 2. And that's mechanical work. And then since you know the mass of the copper piece here, and you know the heat capacitance, you can estimate the thermal energy that's being used here by subtracting the final temperature with the initial temperature that you get from this graph. And by dividing the two, you can estimate the value of J, which is delta W divided by delta Q. All right. Okay, so from here, enjoy the lab, and thank you for your kind attention.